Welcome back. In this section, we're going to talk about dividing one polynomial by another. So the reason why we're going to be talking about division of polynomials now at this late stage is because this is a technique that we're going to need to use when we're factoring higher degree polynomials. We're going to need to factor, and factoring is a kind of division. So some things that we'll do here, we're going to start by just remembering how division works when we're talking about numbers. We'll do a brief refresh as far as long division goes with polynomials. But for the most part, I'm not going to divide polynomials using long division. I'm instead going to use synthetic division, which is much faster. And so I'm showing you long division not because you really need to do it, but because I want you to at least have something as an available option in case you need to divide two polynomials. But for most of what we're doing, synthetic division will be the much more efficient choice. Okay, so first off, just to remind ourselves when we're talking about dividing things, the thing that we're dividing into, that's called the dividend. The thing that we're dividing by, that's the divisor. So for example, if I were to say something like, what is 25 divided by 3? 25 is the dividend and 3 is the divisor. And if you divide out and you find out what the quotient and the remainder are, then you can express that your dividend divided by your divisor should be equal to your quotient plus whatever your remainder is over whatever your divisor is. Which I know that sounds like a lot of words, but really this is something that you've used back in elementary school when you were taking an improper fraction like 37/4 and rewriting it as the mixed number 9 1/4. That's exactly what you did when you were rewriting that one improper fraction as a mixed number. It really was the same thing, since 4 goes into 37 9 times with a remainder of 1, then 37/4 is the same thing as 9 1/4, or 9 plus 1/4. So the consequence to that, of course, is if you're looking back here, we had the statement of dividend divided by divisor is equal to quotient plus remainder over divisor. And if I were to take this equation and if I were to multiply everybody on the left side and on the right side by whatever the divisor is, then on the left side, the divisors in the numerator and denominator would cancel. For the second term, the remainder over divisor, the divisors would cancel. And in the first term, you would have now quotient times divisor. And that's what we have here on the next slide, that going from this equation to this one just came from multiplying both sides of the equation by whatever the divisor is. So just to sort of put things into context again, we had in numbers 37/4 was the same thing as 9 plus 1/4. And if you multiplied everybody by 4, you could say that 37 is 4 times 9 plus 1. That these are two equivalent ways of stating the same answer, or stating the same relationship between our dividend, our divisor, our quotient, and our remainder. Now, the nice thing here, of course, is that if your remainder is 0, then that means that whatever you were dividing by must be a factor. So, for example, we know that 36 divided by 4 goes in 9 times with a remainder of 0. So in other words, 4 is a factor of 36. That's just what a factor is, something that goes in evenly with no remainder. And we're going to look at the same sort of ideas extended to polynomials, that for polynomials divided by polynomials, you could rewrite them as your one polynomial is equal to your other polynomial that you were dividing by times that quotient plus whatever the remainder is that's left over. And it would be true for polynomials as it was for numbers, that if you don't have a remainder, then whatever you were dividing by must have been a factor. Okay, so we'll first do some long division of our polynomials here, but before we do that, we'll do long division just of numbers. So 770 divided by 4, and I'm giving myself lots of room so that I can refresh ourselves as to how we do this. Remember that we begin by asking ourselves, how many times does 4 go into this number? How many times does 4 go into 7? And the answer is it goes in once. Then the next step that we do is to multiply. We multiply 1 times 4. That gives us 4. We subtract. 7 times 4 is 3. And then we bring down the next digit. We bring down the 7. And then we just repeat our process. How many times does 4 go into 37? It goes in 9 times. We multiply. We multiply 9 times 4. 9 times 4 is 36. Then we subtract. And then we bring down. And then repeat again. How many times does 9 go into how many times does 4 go into 10? It goes in twice. 2 times 4 is 8. We subtract, and there's nothing left to bring down, which means that what we have here at the end, since we've divided as far as we can, we've gone into the last digit, that must be the remainder. The remainder must be 2. And that how many times it went in, that was our quotient. Our quotient must be 192. So if we wanted to rewrite things, we could say that 770, our dividend, should be our divisor times our quotient plus our remainder. And in fact, you can double check that 4 times 192, if you were to multiply that out, that's 768 plus 2 more. Yep, that gives you 770. You could also phrase this, and I'll just give myself some more room down here. You could say that 770 over 4 is your quotient plus your remainder over your divisor. So you could also say that 770 fourths is 192. Sorry, I got excited with my numbers there. 192, that's our quotient, plus our remainder over our divisor. So 192 plus 2 fourths. Okay. So that was doing long division with numbers. And again, notice that the process for long division with numbers was asking ourselves how many times did something go in. We then multiplied, we subtracted, and then we brought down. And that's exactly what we'll be doing when we're dividing one polynomial by another. So here I'm going to be dividing one polynomial by another. I've got x cubed plus 2x squared plus x plus 1. Let's write that out. And we're dividing it by x minus 3. Okay, so let's get ready to start dividing here. But before we do, the one thing just to mention is, because it's difficult for us to ask the question of how many times does x minus 3 go into something, we'll ask the easier question, which is how many times does x go into something? So in this case, how many times does x go into x cubed? And it goes in x squared times. We'll then multiply. We'll take x squared and we'll multiply it by all of that, by x minus 3. And when we multiply the two things together, x squared times x, that gives me x cubed. X squared times negative 3, that's negative 3x squared. And now we will subtract. I'm putting brackets around it because I want to remind myself that I'm subtracting both terms. So I have x cubed minus x cubed, which is gone. Then I'll have 2x squared minus negative 3x squared, which is the same thing as 2x squared plus 3x squared, or 5x squared. So we asked how many times does x go in? We multiplied, we subtracted, and next thing that we do is bring down. We bring down the next term, and then repeat the process. So now we'll ask ourselves, how many times does x go into 5x squared? And x goes into 5x squared, it goes in 5x times. We'll then multiply 5x times x minus 3. We multiply those together. That gives me 5x times x, or 5x squared. We have 5x times negative 3, that's negative 15x. And then now we will subtract. I always put brackets around these things again because I want to be cautious. I want to make sure that I'm subtracting not just the first term, but I'm subtracting both terms. 5x squared minus 5x squared is gone, and then I've got x minus negative 15x, which is same thing as x plus 15x, or 16x. And then we bring down the next term and continue the process. So we ask ourselves, how many times does x go into 16x? It goes in 16 times. We multiply. 16 multiplied by x minus 3. 16 times x is 16x. 16 times negative 3 is negative 48. We subtract. And so we've got 16x minus 16x is gone. You have 1 minus negative 48. You have 1 plus 48, which is same thing as 49. And since there's nothing left to bring down, then that means that you are finished, that this is what you've ended up with, your quotient and your remainder. That the quotient here is x squared plus 5x plus 16, and that the remainder is 49. The one other thing that we can say here as a little consequence is that since you have that x minus 3, when we divided it into that polynomial, that we got a remainder of 49, then that means that we have something where x minus 3 we know is not a factor. We know it's not a factor because if it were, then it would have to be going in with a remainder of 0. So although that wasn't really the question wasn't determine if x minus 3 is a factor, nice to notice here that because we found that the remainder wasn't 0, we can conclude that x minus 3 is not a factor. So long division always works. Doesn't matter what you're dividing by. So if I wanted to divide by something that was a cubic polynomial, or divide something by an x squared or by an x to a higher power, I could go right ahead and do all of those with long division. It is kind of a pain. As you'll notice here, the long division that we did took many, many steps. It took a lot of work and a lot of writing to go from beginning to end. Now, in the case where you're dividing by something that's linear, something that's just x plus a number or just x minus a number, then actually synthetic division will be a much faster way, a much faster approach to finding your quotient and finding your remainder. So the way that we set up synthetic division is like this. Instead of writing out all of our terms, just like we did in long division, for synthetic division, we're only going to write out our coefficients. So for our coefficients for our polynomial, we have, and we write them in order from largest power to smallest, and this is already in the standard form, largest power to smallest. So our coefficients are 1 for the x cubed, 2 for the x squared, 1 for the x, and 1 for the constant. That's our first thing. Notice here I had one of every power of x. I had constant x, x squared, x cubed. If I was missing any one of those, if I was missing a power of x, then I would put in 0. So for example, if there was no x squared term, then I would have a 0 as the coefficient for the x squared term. But of course I do have an x squared term there, and its coefficient is 2. Now, the one little twist here with synthetic division is that if you're dividing by something like x minus 3, it's not minus 3 that we'll use, it'll be positive 3. And the reason why we're switching the sign here from something negative to something positive, it's so that it'll make our work a little bit easier as compared to this. Notice that when we were doing long division, after we did the how many times it went in, we had to subtract, subtract, subtract. And subtraction's always a harder operation for people than addition. And that's actually the clever idea behind synthetic division, is that if we switch our sign from, in this case, a negative to a positive, or if it had been a positive, switch it to a negative, then that means that instead of doing a bunch of subtractions, we'll be doing some additions instead. And so, how we do synthetic division is actually really quick and easy. The first move is always that first coefficient, we just bring that down. So that first coefficient, 1, I've brought it down. And then the next thing that we do after that is just a sequence of multiplication and addition. That's the difference. When we did long division, we did multiplication, x times x minus 3 to give us this. Then we did subtraction. Synthetic division is going to be faster because instead of multiplying then subtracting, we'll just be multiplying and then adding. So let's get into that. We have our leading coefficient brought down, and now we'll start our work. And our work will begin with first multiplying 3 times 1, that gives us 3. And then we, instead of subtracting, we add. 2 plus 3 is 5. And then we just repeat the process. Multiply 3 times 5, that's 15. And then we add 1 and 15, that's 16. We multiply 3 times 16, that it multiplies to give us 48. And then we add 1 plus 48 adds to give us 49. And then what we have here at the bottom, we have our remainder term, and then the coefficients for the constant, the x, and the x squared term, and any other higher powers that you might have. So always the last number that you find, that is your remainder, and then your other coefficients that you have are in increasing order of power, from constant to x squared, and so on. So from this, you can say that your quotient should be 1x squared plus 5x's plus 16, and that your remainder should be 49. Now, just compare and contrast this work that we did here with the previous slide. Notice it's the same polynomial and that I was dividing, and I came up with exactly the same answer, just with a lot less work, a lot less writing, and a lot faster. Also less error prone, because people can generally be counted on to add where they can't always be counted on to subtract successfully, myself included. Addition is always an easier operation for people than subtraction, so for making mistakes, less common with synthetic division than with long division. Also notice we didn't have to write any of the powers of x down, just the coefficients, so much less writing, much faster, much easier. Okay, let's do another one here. We've got synthetic division. We want to use that to find our quotient and our remainder when we're dividing this polynomial by x plus 2. So first, I'm going to take my polynomial, and it's already in order from largest power to smallest. So I'll write in all of my coefficients, and anytime that there's a power of x that's missing, the coefficient is 0. So we have 1x to the 5. There are no x to the 4s. There's 3x cubed. There are no x squares. There's negative 1x's, and then there's 1 for your constant term. And I know that I'm dividing by x plus 2. So since it's x plus 2, I'll switch that sign to negative 2. And that my first move before I do anything is to bring down that leading coefficient of 1. And then everything after that is just a process of multiplying and adding. So we're multiplying negative 2 times 1. That would be negative 2. And then we add. 0 and negative 2 is negative 2. We multiply. Negative 2 times negative 2 is 4. We add 7. We multiply. Negative 14. We add. Negative 14. We multiply. Positive 28. We add. Positive 27. We multiply. Negative 2 times 27, that is negative 54. We add, that's negative 53. And so, as always, the last coefficient that you found, that is your quotient. So we know that our quotient is negative 53. So, side conclusion, x plus 2 is not a factor of this polynomial. But back to the main question, what is the quotient and what's the remainder? Remainder is negative 53. And for the other terms, these tell us the coefficients for our constant, our x term, x squared term, x cubed term, and x to the 4th term. So for our quotient, or remainder quotient rather, our quotient should be x to the 4 minus 2x cubed plus 7x squared minus 14x plus 27. So we have a quotient, x to the 4 minus 2x cubed plus 7x squared minus 14x plus 27, and a remainder of negative 53. Okay, so here we've got one other thing to mention, which is, again, same idea that I've mentioned a couple of times so far, which is that if you happen to have a factor, then it goes in evenly. In other words, the remainder is 0. And in other words, you can say f of x is that factor times whatever that quotient happens to be. So for example, you can tell that x minus 3 is a factor of x squared minus 9. And if you were to divide x squared minus 9 by x minus 3, the quotient that you would get would be x plus 3. It would go in evenly, leaving x plus 3. And that's how you can conclude that x squared minus 9 is x minus 3 times x plus 3. So same sort of thing that we're going to do here. We're going to check to see whether this polynomial is a factor of this polynomial. And if it is, then we can factor out the polynomial as x plus 3 times whatever the quotient happens to be. And if not, then not. So the finding out if it's a factor or not, that we do with synthetic division. So starting with 1x cubed, 3x squared, 4x, and 12. We're dividing by x plus 3, so minus 3. We bring down, we multiply, and we add. We multiply, and we add. We multiply, and we add. So this tells us the remainder is 0. That means that x plus 3 is a factor. The remainder is 0, so x plus 3 is a factor. And in particular, you can say that that polynomial x cubed plus 3x squared plus 4x plus 12 could be written as x plus 3 times that quotient. And the quotient would be 4 is the constant term, 0 for the x term, 1 for the x squared term. That would be x squared plus 4. And one thing that you can do now, just to confirm your work, you can actually expand this out and check to see, does x plus 3 times x squared plus 4, does it give you the polynomial that we started with, the x cubed plus 3x squared plus 4x plus 12? And the answer is yes, it does. So this is sort of a nice little idea, and it's sort of foreshadowing for what we're going to see in the future sections for when we start thinking about trying to factor higher degree polynomials. Let's do one more here. We want to check to see if x minus 1 is a factor of this polynomial. So I'll begin with, I have 1x cubed, 2x squared, 1x, and minus 3. And I want to see if x minus 1 is a factor, so I'll use positive 1. And then we'll just bring down, we multiply and add, multiply and add, multiply and add. And so here I can say that the remainder is not 0. So that means that x minus 1 is not a factor of that polynomial. So there we go. So for synthetic division, again, the one thing where it's especially useful is for any case where you're dividing by either x plus a number or dividing by x minus a number, which is going to be all the cases that we're really interested in when it comes to us factoring polynomials. Long division is the more general way of dealing with things, and it is a useful skill to have if you wanted to divide by something that was not just an x plus a number. But for us, for the most part, these are the sorts of things that we'll be dividing by, checking to see if x plus a number or x minus a number happens to be a factor for a given polynomial, and synthetic division is how we'll check to see if it is or is not. Okay, so now one more example here. We want to show that x minus 3 is a factor of this polynomial, and then we want to factor this polynomial completely. So I'll start with this. First, to show that it's a factor, we'll do that with synthetic division. So let's see, we have 6x cubed minus 25x squared plus 16x plus 15. I don't really need the pluses in there, I suppose. Plus 16x and positive 15. And we're dividing by x minus 3, so we'll use positive 3. And of course, what it's asking us to show is that x minus 3 is a factor, so that means we're hopefully going to be getting 0 as a remainder here. If we don't, then that means that we probably did something wrong, because we're supposed to show that x minus 3 is a factor. We're confirming that that's the case. And I don't give trick questions. If I ask you to show that something is a factor, then it is a factor. So I guess let's show that it is a factor. Let's bring down and then start our process of multiplying and then adding. So beginning with, we multiply 3 times 6, that's 18, and then we add up. 18 and negative 25 add up to negative 7. And then we multiply again. 3 times negative 7, that's negative 21. And then we add 16 plus negative 21, that's negative 5. Then we multiply. 3 times negative 5, that's negative 15. Negative 15 and positive 15, they add up to 0. So, okay, that means that yes, indeed, we can confirm that x minus 3 is a factor. And that's because the remainder happens to be 0 when we divide it by x minus 3. That also tells you that f of x can be factored as x minus 3 times whatever our quotient is. And here our quotient happens to be 6x squared minus 7x minus 5. And now the rest of this is asking us to factor f of x completely. And so if we want to factor f of x completely, that means we just need to factor this last little remaining part to factor 6x squared minus 7x minus 5. And we know how we would do that. If we're reminding ourselves to factor something like 6x squared minus 7x minus 5, we would be looking for numbers that multiply together to give us negative 30, 6 times negative 5, and which add up to give us negative 7. And if you're thinking about what numbers multiply to negative 30 and add up to negative 7, that would be negative 10 and positive 3. Negative 10 and positive 3, that multiplies to negative 30. Negative 10 and positive 3, that adds up to negative 7. So this means that that would be able to be split up into negative 10x plus 3x. And then we could factor by grouping, taking 2x out of the first two terms, leaving 3x minus 5. The last two terms I could factor out a positive 1, leaving 3x minus 5, which means that that polynomial, that 6x squared minus 7x minus 5, factors as 3x minus 5, 2x plus 1. So now we can go back and say, well, f of x factors as x minus 3, and then the other part of the polynomial factored as 3x minus 5 and 2x plus 1. And that's as factored as that's going to get, so that would be where we would end with f of x.